Okay, this is section 1.4. This should be the next section in line. We finished 1.1, 1.2, and 1.3. I forgot to bring home a copy of this, so I kind of had to handwrite it, and I'm just going to use this, but it should look just like your notes do. It's just handwritten. So we, in section 1.3, started getting into a little bit of trig, just some basic trig functions, how to put an angle on the coordinate plane so that the vertex is lined up at the origin and the initial side of the angle lies on the positive x-axis. And we know if it's rotating clockwise, that's a negative angle, counterclockwise, it's a positive angle. We looked at how you can find, given the coordinates, any coordinates for any point on the terminal side of an angle, how you can find all of the tricks. If you just get used to drawing those triangles, labeling the sides, then you can, if you've got all three sides, you can find all six trig functions, and that's kind of what we did in 1.3. So we started into some trig. So in section 1.4, we began to look at some basic trigonometric identities, and 1.5 actually takes the identities a little further. So this is typically a section that identities are usually something you do later on, but it kind of just introduces them here, and then later we'll work a little bit more with identities. But so as an introduction to, there's just some identities that you need to remember. You'll remember a lot of them just from common the frequency with how often they come up in problems. Others you might have to make a little more point to commit to memory. Some of them you probably already know. So first of all, before we get into the trig identities, let's just to define what an identity is. An identity in math refers to any equation that is true for all values. So for any replacement value, anything you put in is going to make it true. So for an example, we can start with something really easy. We can say a plus 0 equals a. All right, that will always be true. That's basically called the additive identity, the identity for addition. So it basically is saying that if you add 0 to any number, that number remains unchanged. I could do a plus negative a equals 0. This, no matter what you replace a with, any number and its opposite equals 0. So because these are true all the time for every value, those are called identities. I could say a plus b times a minus b, and there's nothing special about a and b, that's just the variables I chose to use, equals a squared minus b squared. No matter what you put in for a, this is true all the time. So those are just some examples of basic identities. Now, we, and some of them have names. We have another one you could do a times b plus c. That would always equal a times b plus a times c. And you know some of these properties as is identity for addition or additive identity. This would be the additive inverse identity. This would be this distributive property. But those are all examples of identity because they're all true for every value, no matter what you replace a or what you replace a, b, or what you replace a, b, and c with. And the last one, you will always, these two sides will always be equal. Okay, so now let's jump in and look at some trigonometric identities. And I think I left, these are actually called reciprocal identities. All right, so reciprocal identities are exactly what they say they are. They are just, every trig function is reciprocal of another function. So for example, and if you just remember, sine and cosecant kind of pair together. Sine is equal to 1 over cosecant. Cosecant is equal to 1 over sine. So they're just reciprocals of each other. Cosine is 1 over secant. Secant is 1 over cosine. So these are reciprocals of each other. So if you have a tendency to get these mixed up, if you can't remember, does cosecant go with sine or cosine? Just remember it's the S with C, the C with the S, C with the S, S with C. So you'll never have the S with the S, or S with the S, sorry, or the C with the C. You always will have the sine with the cosecant and the cosine with the secant. And then of course tangent and cotangent, those are pretty easy to remember. So these are all, every single trig function can be written as the reciprocal of another trig function. So just remember which ones to go with which. So that will help you if you just remember sine S goes with the C, and then the C and cosine goes with the S and secant. All right, so it's pretty simple here. It says if sine of, in these examples, if sine of theta is equal to negative 2/3, find cosecant. Well, cosecant is just a reciprocal of sine, so cosecant would just have to be reciprocal of negative 2/3 is negative 3/2. All right, so nothing difficult there. If tangent is equal to 1/8, to find cotangent. Well, again, these are just reciprocals of each other, so the cotangent, if the tangent's 1/8, the cotangent would be 8/1, or 8. And if secant is 7/3, cosine is the reciprocal of that, which would be 3/7. So the sign will not change. It'll be whatever. When you do the reciprocal, it doesn't change the sign. But if the original value is negative, the reciprocal will also be. Okay, so then we go on to another set of identities in trig, which is called ratio identities. So ratio identities really specifically refer to tangent and cotangent. So tangent can always be written as sine over cosine. Cotangent is a reciprocal of sine, so the reciprocal of sine over cosine is cosine over sine. If you want to think about this one in terms of the coordinate plane, let's say I've got an angle here, and this is x, and this is y, and this is r. So if I were to write the tangent of the angle theta, which is opposite over adjacent, so this would be equal to y over x. Then I can show you that the sine, which would be y over r, so this would be equal to y over r divided by cosine, which would be x over r. If you simplify this, y over r divided by, so when you divide, remember you multiply by the reciprocal, so I'm going to change that to multiplication, r over x. So dividing by x over r is the same as multiplying by r over x. So when these reduce out, you get y over x, which is the tangent. So, all right, so that's the only two, that's all there is for ratio identities. Just remember that tangent can be written as sine over cosine, so think of that as y over x. Cotangent can be written as cosine over sine, which would be x over r, or sorry, x over y. All right. So an example using the ratio identity. So it gives me cosine to be negative 3/5, sine to be 4/5. So if I'm trying to find tangent, all I really need to do is take, it is sine over cosine. So I'm just following directly what the identity says. And that sine is going to be 4/5, that goes on top, divided by the cosine, which is negative 3/5. And simplify that, you're going to have 4/5 divided by, or multiplied by the reciprocal, so times reciprocal of negative 3/5 is negative 5/3. And those divide out, and I end up with negative 4/3. And then it asks us for cotangent. So cotangent, so I could do the same thing, but it'd be a whole lot easier just to take, since I know the tangent, and I can use these reciprocal identities. The cotangent is reciprocal of the tangent, so the reciprocal of negative 4/3 is going to be negative 3/4. All right, last group of identities, and these are very common, so especially this one right here. These are called Pythagorean identities, and I'm going to show you why they're called Pythagorean identities. So basically, they're derived from the Pythagorean theorem. So if I were to draw the coordinate plane here, so let's just do quadrant 1 here. So this would be x, this would be y, and this would be r. So the sine of the angle theta here, opposite over hypotenuse, or y over r, so y over r squared. and the cosine x over r squared. All right, and so if we squared the top and bottom, this would be y squared over r squared plus x squared over r squared. And then we can add these together since they have the same denominator. The numerator would be x squared plus y squared or y squared plus x squared. Now, how does that equal 1? Well, using the same triangle, remember that the Pythagorean theorem holds true, so x squared plus y squared equals r squared. So I know that if this is a right triangle, then x squared plus y squared has to equal r squared. So if I replace the x squared plus y squared with r squared here, then I end up with r squared over r squared, which is 1. So basically, bottom line, anytime you have sine squared plus cosine squared, it's always going to equal 1. Now, the other two are a little bit less common to use, but I could derive these super easy. If I just took this one and let me just come up here and I'll show you how we come about this. So we've already proved that this is true. All right, so I want to end up with secant squared here. So to make this be a secant squared, secant is 1 over cosine. So what if I just divided this by cosine squared? Now, I can't just divide this by cosine squared unless I divide everything by cosine squared, so that's what I'm going to do. All right, well, what is sine over cosine? I'll go back to your ratio identities. Tangent, sine over cosine. We just got through defining that as a ratio identity as tangent, so I could replace this as tangent plus cosine squared over cosine squared. Anything over itself is 1. And anything 1 over cosine is secant, so 1 over cosine squared would be secant squared. And so that is just by taking this one and just dividing everything through by cosine squared, we derive one of the other forms of the Pythagorean identity. Tangent squared plus 1 equals secant squared. Same thing with this one. If I start with my basic sine squared plus cosine squared equals 1, this time I want to end up with cosecant over here, cosecant squared. So I would want to divide 1 over sine. Cosecant is 1 over sine, so I would want to divide by 1 over sine squared. I could do that as long as I do that to every term. Okay, so I got sine squared over sine squared. Well, that's 1, so it's kind of reversed, but that's that. Cosine over sine. So remember what cosine over sine is. Go back to the ratio identities. Cosine over sine is cotangent. So this would become cotangent squared, which is here. So it's kind of reverse the order. And then 1 over sine is cosecant. So this becomes 1 over sine squared becomes 1 over cosecant squared. So that's where this comes from. So these are all just different forms of this. Remember also that if you have sine squared plus cosine squared equals 1, if I subtract the cosine squared over, if I started with sine squared plus cosine squared equals 1, and I subtracted cosine squared over to the other side, I would have sine squared equals 1 minus cosine squared. And I could have, instead of subtracting cosine squared over, I could have subtracted sine squared over, and that would have given me cosine squared equals 1 minus sine squared. I could do that with every one of these. It's just write them in different forms. So I could write them in 3 different forms. So the original form, the second form, and the third form. There's 3. And I could do that with every one of them. I could subtract tangent squared over and have secant squared minus tangent squared equals 1. I could do the same thing here. So what I really would recommend you is just when you see squared functions, sine, cosine, tangent, or any of the reciprocals together, is think in terms, when you see those functions squared, is there a Pythagorean identity that's going to come into play? Will one of these work? So usually, if you see a sine squared plus cosine squared, you can interchange that with 1. If you see a 1 minus cosine squared, that's the same thing as sine squared. If you see a 1 minus sine squared, that's the same thing as cosine squared. So that's where those are going to come into play. All right, so also a little notation thing here. It talks about you, when you write, notice how we write sine squared here. But notice that that means this. So if we put the squared on the angle, it would look like the angle was squared. It look like you were taking the sine of the angle squared. And that's not what we want. We want sine theta times sine theta. That's what this means. So this basically indicates that sine theta is multiplied by itself twice. If you just wrote it like this, slide it over there. If you wrote it like that, that would mean, if your angle was 30 degrees, it would be the sine of 30 squared, so it would be the sine of 900. That's not what we mean. We mean we want this with the sine of the angle. Take the sine of the angle first and then square it. And so the common way to write that is to put the squared on the sine, so that way we know it's not the angle that's squared, because there may be a time where you actually do want to square the angle. All right, the last two examples, we're going to see if we're going to use the Pythagorean identities here in this problem somewhere. So, so it's given me the sine is 3/5. It terminates in quadrant 2. And it wants me to find the cosine and the tangent. And I can do it using what we did in section 1.3. But I'm going to try to use the identities since that's what the section's about. I may show you the other way to do it too. So let's draw it out. It's in quadrant 2. So it's over here. Always draw your triangle back to the x-axis, not to the y-axis. So I have the sine. So this is the ratio of y to r, or opposite to hypotenuse. So this would be 3 to 5. If I need this side, this would be 4, because 3, 4, 5. If you don't remember, if you don't know those, you can always do Pythagorean theorem, but it's a common triple. And so I've got the sine set up. From that, I was able to find the cosine. I was able to find the other side. And now I can find any of the values I want. So it wants me to find cosine, and so I could do. I'm going to go do this. Is not the way I'm not using the identities as I do it this way. But I just want to kind of draw it out. But I can do it just using what we already knew before this. Is the cosine then would have to be x over r, which would be 4 over 5, and then the tangent would be y over x, opposite over adjacent, which would be 3 over 4. Now, I'm going to show you how to use the identities to get that. So let's say I'm given sine and I'm trying to find cosine. So using this identity right here, what if I said sine squared plus cosine squared equals 1? So if you have an angle and you take its sine and its cosine and you square them and add them together, this should always equal 1. So let's replace sine with 3/5. We know the sine of theta, so sine is 3/5. So if we want the sine, it's squared though. So sine of 3/5 squared plus, I don't know cosine. That's actually what I'm trying to find. All right, so if I could solve this for cosine, I just use this identity to do that. So let me square 3/5. So 3 squared is 9, 5 squared is 25. And then I'm going to solve for cosine, so I'm going to subtract 9/25 over. All right, so I'm going to think of 1 as 25/25, 25 over 25. So 25 over 25 minus 9 over 25 would be 16 over 25. And then I've got to undo the square, so I'm going to square root. So I would actually end up with plus or minus 4/5. Square root of 16 is 4, square root of 25 is 5. But because it's in quadrant 2, I can rule out the fact that cosine, this is actually negative. Missed it there. So it should be the negative, so it would be negative 4/5. So I showed you both ways. The same thing we got over here. So I used the Pythagorean identity here and did it because I knew sine. I could just plug that in and I was able to solve for cosine. Over here, I just drew it out, labeled the triangle, found the missing side, and used that method to find the missing values. All right, the last one, G. Again, this time they give me cosine, and it tells me it terminates at quadrant 2. So if I'm going to use the identity, sine squared theta plus cosine squared theta equals 1. So I know cosine, so let's replace cosine with, so sine I don't know, that's one of the I've got to find all 5 of them, so it's one of the 5. All right, so I've got that. Cosine is -5/13. All right, and then I'm just going to solve it for sine. So I'm going to square the 5 squared is 25, 13 squared is 169. All right, and so now I'm solving for sine, so I'm going to subtract 25/69 over 169, sorry. All right, so let's combine these together. So what is 1 minus 25 over 169? So we need to think of 1 as 169 over 169, and 169 minus 25 would be 144 over 169. Okay, square root. So sine theta is equal to plus or minus 12/13. But now we know that we're lying in quadrant 2 and we're finding sine. So sine in quadrant 2 is positive. You're up here going up. So positive, it's just 12/13, positive. Do it that way. All right, then I've got to find the other. So I've got cosine. Now I've got to find tangent. All right, so tangent, I could do this identity. I could use this identity here. Since I have cosine, I could flip it over and have secant and then solve for tangent. And I'll just do it that way since that's what we're practicing here is the Pythagorean identities. But I could also just take the sine over cosine. That would be the quickest, honestly, way to do it. So we use the ratio identity. So remember tangent, if you go back to tangent, it is sine over cosine. So sine, I could take 12/13 sine divided by cosine, which is -5/13. And if you do the math there, you got 12/13 divided by or multiplied by the reciprocal of. So flip this one over, -13/5. Divide out. Okay, so tangent should be -12/5. And then to get the other 3, it's just going to be cotangent, secant. I'm just going to flip those over. All right, so cotangent is going to be the reciprocal of -12/5, so it'll be -5/12. Secant is reciprocal cosine. Cosine was given, so -5/13 would be -13/5. And the sine is the reciprocal, cosecant is reciprocal of sine, and vice versa. So the reciprocal of 12/13 would be 13/12. All right, so there's my one there they gave me. There I found this one, 2, 1, 2, 3, 4, 5. So I found all the other 5 functions. All right, so in this section, that's really what it comes down to. Let me just kind of reflect back over the identities. So these, you probably know these pretty well right now. If you don't, it won't take that long, especially these 3. It might be the ones you don't know. The ratio identities, remember, tangent is always sine over cosine. It's y over r divided by x over r. The r's cancel out and you get y over x, which is what we know tangent is. Cotangent is just the reciprocal of this, so it's going to be cosine over sine. And then the Pythagorean identities, when you have your functions and they're squared, so like sine squared plus cosine squared equals 1, or any form of that, tangent squared plus 1 equals secant squared, and cotangent squared plus 1 equals cosecant squared. These are going to come up a lot, especially this one. And you're going to want to remember that. When you see that sine squared or that cosine squared or both of them together, you just come back to this identity and look at it because until you get it down, because it's probably going to be used at some point in the problem.